Hello everybody, I'm back again to talk about more colligative properties. I'm going to focus on boiling point elevation and freezing point depression. Those are two major effects that we should study. So let's look at this, and the relevance, we have two equations here. They're very similar in form. This is for freezing point depression. You observe this winters in the north, Vermont, New York, and so forth, when you see people putting salts of different type, usually it could be sodium chloride, magnesium sulfate, what have you, on ice. What they're doing is by increasing the solute concentration of the medium, what it will do is foster the ice melting at a lower temperature, which is great. You can have you can clear a walkway like that. Boiling point elevation. If, for example, if you put salts, NaCl, in water and you boil it, it'll boil at a higher temperature. Besides making the food salty, you can cook the food at a higher temperature. Of course, these both have environmental ramifications and so forth in nature. The equations are very simple. The interpretation is usually what gets people. The freezing point gets lower with the addition of salts and other types of solute particles. The boiling point elevates from that. These are the equations where you calculate the amount of depression you have or the amount of elevation you have, and that's where usually people make a mistake with this. The formula is very simple. In this case, you have constants. This is a freezing point constant. This is a boiling point constant. Typically, these are in terms of degrees Celsius per molal. There's a table of these on approximately page 15 of your note sets. So M is molality. In both cases, the equations are very simple. So we use molality, appears to be a good metric for concentration to model this effect. And it's similar in this equation over here. I is another thing that confuses people. I is called the Van Hoff factor. The Van Hoff factor, I think there's a little apostrophe there. The Van Hoff factor relates to the number of particles you get for every solute particle. So for example, if let's say your solute particle is a non-electrolytic species, let's say you're adding some methanol to the solution, that doesn't ionize, and so I is equal to 1. 1 molal of methanol does not have to be adjusted by any kind of multiplicative factor to say that it forms more particles than just the 1. So 1 molal solution would just have a 1 multiplier, or whatever the molality is, would have a multiplier of 1 in front of it. You really don't have to write it in at all. If you have something like NaCl in solution, and let's just focus on in water. In water, it's going to break apart into two aqueous phase ions, the sodium ion and the chloride ion. So for every 1 unit of NaCl, which is really the formula unit of it, you get 1 particle, 1 ion of sodium and 1 particle or ion of chloride. And so here, the expected value for I is equal to 2. Where people get a little bit of a problem with this is sometimes you deal with plenty of materials that are where it's not so simple. So if somebody says potassium sulfate, remember that sulfate ion is 2 minus. So this would give you 2 potassium ions, I should say, in the sulfate ion. So here I would be equal to 2, 3 would be equal to 3. These are expected values. What happens in nature, it's a function of both the molality and the temperature, is that I experimentally may vary a little bit from that. For example, there's a table, page 15 or 16, I'll let you find it, but there's an expected values are as written. Sometimes experimentally you might see, like for example, at a 0.050 molal solution of sodium chloride at 25 degrees Celsius, and I'm doing this because I looked at the table before, I actually ends up being 1.9. You actually have a little bit of clustering of ions in that solution, and I have a diagram, a depiction of that that's nicely artistically rendered you can look at. But the point is that it can vary slightly. Usually it's slightly less. But it's a function of molality and temperature, meaning it's something you can't always readily look up. On exams and problems, I'm going to have you work with the expected values because it shows me you understand stoichiometry and polyatomic ions and so forth. So on an exam, if it's NaCl, the Van Hoff factor would be 2. If it's potassium sulfate, the Van Hoff factor would be 3. Let's take something maybe a little more confusing. Let's take ammonium phosphate. That breaks apart into, you get the 3 in there, 3 ammonium ions. And we would get the phosphate, that's -3. That's one of the more highly charged species we deal with. So here I would be equal to 4. I is equal to 4. The Van Hoff factor is 4. So the thing is don't forget your polyatomic ions. They're not trivial for a lot of problems we work in here. Know how to break apart these formula units and know when things don't break apart. When you have a non-electrolytic species, that's actually a really easy problem to work. I'll leave the equation up for the freezing point. So let's work the problem. So let's see here. What did I work? I said let's say using the expected value. So I tell you in the problem use expected Van Hoff factors. I is the Van Hoff factor. I say calculate the freezing point. I'll call it FPD, the freezing point depression. I'm going to calculate both the depression and the freezing point itself of the solution when you have a 0.0350 molal aqueous, so it's going to be aqueous solution of sodium sulfite. So we have sodium sulfite, it's aqueous. And so what we're going to do here is first let's just show what this goes to. This is going to go to 2 sodiums and the sulfite. That's terribly written. Let me get a piece of paper and erase that. So we have I is equal to 3 here. We have 0.0, and also we're told, if you don't know this, water has the freezing point. I'm going to use it to 2 places behind the decimal. I would tell you that on the test to give you a degree of accuracy with your problem. This is the normal freezing point of pure water. So just simply delta T is equal to 3 times 0.350 molal. Then you go to the table and you look up KF. KF, this is 1.86 degrees Celsius per molal. So the molals cancel. And we're left, provided I punched in my calculator right. What did I get here? I'll keep a couple extra sig figs here. Let's see here. 1953 degrees Celsius. That is not the freezing point. A lot of people get this wrong on exams, and I actually checked for this. That's a misinterpretation. What you have to do to get the freezing point of the solution, you understand it's depression. I'm not going to have you memorize a fancy formula for this. Just simply take the freezing point of the fluid of interest. This will be the water, and then you subtract this value. It's a freezing point depression. And so that's going to be equal to negative 0.20. Because we got a 5 here, I'm going to round it up to a 2 degrees Celsius. So it goes down slightly. It goes down slightly. So if you obviously add more salt, you increase the molality. You could increase this up to probably a degree or so. You could definitely make a 0.350 molal solution of sodium sulfite. I'm not sure what the concentration limit is until it starts to precipitate, but you could definitely go up an order of magnitude, which could be significant. So If we want to calculate out the boiling point elevation of the same solution, same type of problem. So we would have in that case delta T, and I'll tell you that the boiling point of water, I'll put at 100.00 degrees Celsius. Delta T would be IM KB. You have to go to the table to get this constant. It doesn't really have any fancy names, just called the boiling point constant. So we got a factor of 3, because again we're dealing with Na2SO3, 1 sulfate ion, and 2 sodium plus 1 ions. The molality was 0.030 molal, and then I have to look. I have no idea what the KB value for this is. It's usually a little smaller. So we have 0.51, let's see here, molal degrees Celsius. And so what we have when we multiply that together, I got delta T is 0.05355. I'm keeping a couple extra sig figs there. So that's not the boiling point. It's going to go up. So T boiling for the solution is going to be 100 degrees Celsius. Of course, you could adapt this to Kelvin or any other scale. 100 degrees Celsius plus 0.05355. And I should put a little degrees Celsius here. Degrees Celsius. Let's add them together, and you're going to get to 2 places behind the decimal. We'll keep it that this. I'm giving you this value. So we're going to get 100.05 degrees Celsius. So it goes up slightly. Could you make it more pronounced? Yeah, you could add, you could go up a power of 10 again. Not as dramatic of an increase as it was a decrease, because the boiling point constant is quite a bit lower. So those are 2 colligative properties. And again, if this was a substance, like let's say it was, we added some kind of a substance like a sugar. Let's say we had a 0.0350 molal solution of fructose. In that case, I would be equal to 1, and you can repeat both of these calculations with I equals 1. In this case, you're going to be subtracting the freezing point depression, subtract that from 0, and in the case of the boiling, you add it to 100 degrees Celsius. And again, this is, I'm doing it with water. This is totally applicable to other solvent systems, as long as the stuff dissolves in there. I mean, that's obviously, you have to be able to make a solution for this to work. I choose water a lot because it's just so relevant for us. You know, most of us are going on to medical or dental school, or you're into environmental science. So water is obviously an important substance, but certainly, you know, including when you take organic chemistry, these same principles apply. And there'll be problems in the notes that definitely have organics in it. I just wanted to use water. And so at any rate, on that note, this covers up, this covers those 2 colligative effects. We're going to talk a little bit about osmotic pressure, which they often is put with colligative effects. I really consider it's more of a diffusion-related phenomenon. You could argue it's colligative. I'm going to treat it as it's a different subset of phenomena, and that's important. Plant biology, human biology, cell biology, including bacterial, osmotic pressure is of importance. So we'll definitely talk about that. So these are the colligative effects, and some of them, and it's important, very practical chemistry. So on that note, I'll let you go. Maybe I'll make another video today. We'll see.